You didn't knock the camera down? No,
I'm sorry, my voice.
It's okay, man.
I had some headache. My voice is bad because in Chinese, yeah. Yeah. So keep this.
你可以说慢点，没关系。
Okay, let's speak slowly. In Thursday, sports is ready. So in Thursday, we are free. So you can go to attend the sports and keep fit. Yeah. So my college tell us 晒太阳 keeping shine is very useful. Okay, in former class, we studied in branch instructions. Branch instructions, we find how do we know if an instruction is a branch. You can find check the green sheet is the answer. So you can find green sheet is a rule. Green sheet has many rules in green sheet. So you can find in order, OP code, function 3 have same fields, but in text, look at that they all have the same OP code. So this is very important. You can find they all have the same OP code. If they have same OP code, they are same OP. Because the OP code is a uniform for the instruction. So we should also try to make sure the other instructions have the same one. So same OP code is very important. Okay, you can see branch instructions. Let's describe our desired behaviors in words. If we are a regular instruction, we choose PC at 4 because the 4 is the size of the instruction. So the PC at 4 is round and round, step by step. Every step has 4 bytes. If we are a branch instruction, we have choose ALU out signal. So you can find if we are a regular instruction, we have set PC selection equal 0. If we are a branch instruction, set PC selection equal 1. So you can find PC selection. This signal is very important for the instruction truth. We can identify a branch instruction by doing an equality check on the OP code. Here's our sub-circuit. So in logic, you can find this is PC selection. So this circuit isn't and isn't all. This circuit is 3 truths. We can see jumps. Which instructions are our jump instructions? We can find they have JALR, JAL. This is jump instructions. In order, OP code, function 3, they can become hex. These are different, so no easy generalization here. Same as with branching, through we can do an equality check on the OP code using a calculator. So you can find the calculator is very useful and equal to the circuit. We'll have to do 2 separate comparisons here. So this circuit equal comparison. You can find the results. The results are more, equal, and less. So this circuit, the output of this circuit are more, equal, and less. which of the following circuits is the correct PC selection for jump. We can see the A and B are very similar. You can find this is different. The others are same. You can find this is N, this is O. So you can find I clicker. This is one OP code, this is one OP code. According to comparators, we can find the two input signal is the input of N or O. This is O and operation, this is N operation. We can find N and O. N if the two inputs is 1, the result is 1. If the two inputs have 1, 0, this is the result of 0. This is O. If the inputs have 1, the result is 1. So we can find this is the result need the two input of 1. The result of all operation needs 1 input. So this is a different result. We find putting them all together, we can have a regular instruction or a branch instruction or a jump instruction to combine all our signals together and return the functionality of each individual piece. We are all there. You can see describing your circuit aloud and keying in on the words you use might be a helpful design or debugging strategy. If any of the sub-circuits are true, PC selection will become 1. Otherwise, it will be 0 because we only have sub-circuits for the branch and the jump cases. All normal instructions will have PC selection equal 0, while branch jump will have PC selection equal 1 and result. So this is the final circuit. We can find this circuit has 1, 2, 3 OP code, and these two inputs is the all operation inputs. This is the final circuit. So if we have the final three OP codes, we can find the PC selection as final circuit. Okay, you can find the control signals is big picture. This is the description. Control signals are how we get the same hardware to behave differently and produce different instructions. For every instruction, all control signals are set to 1 of their possible values or an intermediate value, indicating the control signal doesn't affect the instruction execution. Each control signal has a sub-circuit based on 9 bits from the instruction format. This has upper 5 Fox 7 bits, lower 2 are the same for all 61C instructions, all Fox 3 bits, and 2 second upper opcode bit. This is for control signals. Okay, in the image, we can find the add operation has control signals. We can find the red arrows are related control signals for add operation. So if we have some control signals for some operations, the signals must be related to every component. Add, we can find should we execute the next instruction or jump control flow to the address given by our ALU output. We aren't a branch or jump, so the PC selection equals 0. This is the first position in the image. You can see in this. In the second position, you can find the IMM selection. Red WEN is the second position of this position. So, how do we want to assemble our immediate? You can find we don't care about this signal. We find IMM selection equal random. Do we want to write one to our destination register RD or not 0? This is add should write. So the red WEN, the signal equal 1. This is the third position is BRUN. BR is branch. When we compare our RS1 and RS2, should the comparison be signed 0 or outside the 1? We can find that we aren't doing a branch. This value doesn't matter. So the BRUN equal random. The A selection, B selection, and ALU selection is the last position in the list for ALU. The memory RW and WB selection is for DRAM and this component. So you can find these three signals. Which OPNs do we want to operate on? You can find add, need, or requires RS1 and RS2. So in assembly language, add operation is simple, but for add operation we need RS1 and RS2. These are two registers for add operation. So you can find in C programming we need variables. In assembly language we need registers. This is same and similar. So you can find what operation do we want to perform? Add equal add. ALU selection equal add. So this is the signal and the mechanism. ALU selection we can find for diagramming purpose. We set ALU selection on examples and exam questions to an English value. These are add, sub, or for example. If your CPU, it will have a binary value, and so will all other signals. The mapping between English words and binary words depends on how you build your ALU. In the former class, we have discussed how to build your ALU is very difficult, and build your ALU is by instruction set, and the instruction set, the size of instruction set is very important for CPU. So how to build your ALU is very important, and in Chinese we call 谨慎. 谨慎. 慎重. Yeah. So we can find they give us the binary values depends on how you build your ALU. So you can find binary values is the mechanism of ALU. These mappings are arbitrary. As long as you are consistent, all AND-based instructions have the same ALU selection. Things will work just fine. So these are two last signals, memory RW and WB selections. Memory RW equals 0, WB selection equal 1. You can see, are we reading or writing memory? Is memory RW. What value do we want to write back to RD is WB selection. So you can find we can merge control signals to one array. You can find here are the signals are the values we've compiled for our AND instruction. You can find this is 1 bit and the green is left 3 columns. The orange have right 9 columns. So the green is input, the orange is output. Okay, this is one operation control signals in for AND. This is for several operations. We can find in add, sub, LW, SW, BEQ, BNE, BLT, just so on. You can find in the table they had 3 inputs and 9 outputs. So the format of several operations are same format. Okay, this is a 9-bit ISA. ISA, we can find instruction set architecture. So if we have same format for operation, we have same OP code, the format of OP code, but the number of OP code is different. Okay, this is control construction of options. We can find 2 sections. One is ROM. ROM is read-only memory, so ROM is very popular. Read-only memory, regular structure, like previous slides table. We can find it can be easily reprogrammed. So in popular, we understand the ROM is read-only memory, but in particular condition, the ROM has written. So you can find popular when designing control logic manually. So we can find manually. If we have some manually methods, we can write data in ROM. Combinational logic. Today, chip designers use logic synthesis tools to convert truth tables to networks of gates, are not easily changeable because requires modifying hardware, but likely less expensive, more complex. Yeah. So this is not good idea. ROM-based control. You can find this is ROM. If you will become an engineer in embedding, you can find you are related for chips and chips. So the ROM is the popular chip. In our cell phone, the ROM have existed more and more. My cell phone, the size of ROM is 2.8 and 2.56. This is roaming memory.
Yeah.
This is
RAM
memory.
Read-only memory.
Yeah. This is storage memory. So My cell phone is Huawei. Huawei, the running memory has 8. The store has. So the size is enough for future 3 years. In future several years, we can find the size of ROM has become more and more because the need of software become big and big. So the ROM you can find this is the sum, the output. This is output because error is from right. This is input because error is become in. So this is the control. ROM Controller Implementation. We can find the control word for add, for sum, for all. We can find this is address decoder, and the controller output have included PC selection and M selection. For example, address decoder is a very useful decoder. You can find according to the inputs, we can decode some operation. So the OP code is the decoder inputs, the inputs of the decoder. Okay, we can find the performance analysis, pipeline the execution, and the pipeline the data path. So you can find the pipeline is important term for lecture 13. Okay, instruction time is very important. We can use this image to show instruction timing. In Chinese we call 时序图. In English we call timing. In Chinese we call 时间序列. So timing is correct. Yeah. 时间序列. So from the left to the right, time is computed. Yeah. So timing is the correct term. So we can find the PC signals has early signals, and the instruction fetch and the instruction decode and the execute ALU and the memory read. So we can find 1, 2, 3, 4, 5. This 4 timing has different timing. The PC signals is earlier than other signals.
Program counter.
Yeah, because we need PC signals.
Yeah.
We can running and running. If we haven't PC signals, the running, the instruction timing isn't
If there is no PC, they don't know the next instruction.
Yes, you can find 1, 2, 3, 4, 5. The 5 periods. Instruction fetch, decode, execute, memory, and register write. So this is the timing of instruction. So this is the 时序. Yeah. So you can find this is the signals. Okay, for pipeline, we can discuss timing. You can find in this PPT, we can find this is the image. You can find IF is the first step, and this is instruction 1, this is instruction 2, and you can find ALU, ID, memory, WB is others terms for instruction 1 or instruction 2. So you can find the performance measures in our example. CPU executes instruction at 1.25 GHz. This is equal 1 section every 800 PS. Can we improve this in performance? This is quicker response time. So one job finishes faster. This is one question. More jobs per unit time. This is 2 questions. Longer battery life. This is 3 questions. We can find that this is transportation analog. We can find this is sports car. This is bus. According to the popular minds, we can find the sports car is faster than the bus. So we can find a sports car has less passenger, but sports cars have less travel time. So the bus has more people and have more travel time. This is one example because these two kinds of cars are different. Computer analog, we can find the transportation. Computer, we can find trip time, program execution time, latency, time to update display, throughput. We can find the number of server requests handled per hour, energy per task. You can find how many movies you can watch to battery charge or energy bill for a data center. Energy per task is very important for current world. You know, the famous company is Tesla. Yeah. Tesla is very famous in computer in the battery charge cost. You can find because I had tried Tesla cars in several before 1 week. We find the Tesla we can find the help of Tesla drive is very useful and powerful. If you sit as the driver position, you can find if you open the driver system, you can't need drive. The car can drive automatically. Yeah, but the automatically degree is combined. If we have full service for Tesla, you can find the car can this and this. They can do every position and every columns. But if you have basic service degree, you can find the cars can follow one car step by step. This is enough for China. In China transportation, you can find follow by follow. Yeah. You safe and if we have drive in early and last and we call 早晚高峰 in early so many cars, so we call 高峰早高峰晚高峰. So we find the battery charge cars can need small energy to drive the car. So if we have drive popular cars, Yeah, what is the word of chill? You drive popular cars. We had to add this energy. This is one battery charge. This is a chill for popular car. So we can find the charge. Yeah, chill need more and more. So the battery
gasoline indeed.
the battery technique is very, very important. So this company has become power and power. In China, this company has
in my country
in Shanghai of China, Tesla has one product and product more and more battery charge costs.
in my country most of them are CO. Yeah.
So the battery charge is we need less because the battery has different charge.
Yeah.
So the charge itself we can find if we don't use the A, we can find the battery charge are more time. This is ROM of processor performance. We can find this is one formula. Time per program equal instruction per program, multiple cycles per instruction, multiple time per cycle. So this is the result of time per program. So time for program is one important term. One program needs how many times in one program is one important term. Okay, instruction per program. Instruction per program we can find it is determined by task, by algorithm, by programming language, and compiler, instruction set architecture, and the input. So we can find per program need how many instructions per program is a very important term. Clock cycles per instruction or CPI is another term. We can find ISA and processor implementation or microarchitecture. For example, for our signal cycle RISC-V design, CPI at equal 1. CPI is cycle per instruction. So you can find cycle per instruction. The red skew is CPI. Complex instructions, we can find the CPI can more than 1. And in CISC CPU, CPI has more than 1 is popular. Superscalar processors, we can find the CPI can less than 1. So CPI can equal 1, more than 1, and less than 1. This is time per cycle. This is frequency, 1 divided frequency. So this is the time. This is the time numbers. You can find the processor microarchitecture, processor critical path, and this is become technology and the power buckets. So time per cycle is the last term. So you can find the speed track trade-off example. We can find this is processor A, this is processor B. Processor A has 1 million instructions. Processor B has 1.5 million instructions. The average CPI processor A is 2.5. Processor B is 1. Clock rate, you can find the processor A the clock rate of processor A is 2.5 GHz. Processor B, the clock rate F is 2 GHz. So the execution time in processor A is 1, in processor B is 0.75. So processor B is faster for this task, despite executing more instructions and having a lower clock rate. So each instruction is less complex. So you can find processor B is faster. This is energy per task. So you can find this is capacitance and supply voltage. This is some example. Energy trade-off example, you can find the next generation processor has less than energy consumption. Energy consumption is very important and related to several devices. Significantly improved energy efficiency thanks to you can find more flow and the reduced supply voltage are effective. Energy iron law, you can find performance equal power multiple energy efficiency. So you can find energy efficiency is key metric in all computing devices. Metric is standard. Energy efficiency is very important, and in Tesla you can find the energy efficiency is very high. So you can find energy efficiency is tasks per joule. And for power constrained systems, you can find it is need better energy efficiency to get more performance at the same power. For energy constrained systems, need better energy efficiency to prolong battery life. So the battery life is important for people and persons. We can find too long battery life, too powerful the device. So the battery life is very important. This company can product too long battery life cost. In longest travel, one prolonged battery life is 5 plus kilometers. So you can find this kilometer. This travel is long, but this is try to long and long because China is very big.
Yeah.
In several countries, this travel is enough, but in China this is not enough. You can find from Changsha to Wuhan, you can find the travel is 350. From Changsha to Guangzhou, you can find the travel is 800 or 900. From Changsha to Shenzhen, you can find the travel is more than 1 million.
1,000.
Yeah. 1 million. 1,000.
Yeah.
From Changsha to Shanghai, this travel is long.
Yeah.
But the travel in China is quick. From Changsha to Xi'an, you can find you must sit 5 hours travel. You can arrive Xi'an. From Changsha to Beijing, the quickest the quickest travel is less than 6 hours. So if you want to travel to any other cities, you can choose travel. You can choose airplane. This is pipeline execution. You can find the pipeline analog is during launch. You can find this is some image, some signals. He tells us washer need 30 minutes. Dryer need 30 minutes. Folder takes 30 minutes. Stasher takes 30 minutes to put clothes into dryers. So you can find this is different steps. So he wants to give and steps by steps. This is sequential laundry. You can find sequential laundry takes 8 hours for 4 loads. 1 load finish every 2 hours, and the jigging is up till 2 a.m. You can find 1, 2, 3, 4. DSSG is different and different steps. So this is task order. So every steps need 2 hours. The 4 steps need 8 hours. So this is sequential laundry. This is pipeline laundry. We can find pipeline laundry need 3.5 hours for 4 loads. You can find from 6 p.m. to 9:30. You can find the 4 steps can complete. You can find in this sequential laundry, so every step has different steps. But in pipeline laundry, so every step has the same steps, and 1 load finished every half hour after the first load, which takes 2 hours. So you can find after 2 hours from 6 to 8, these 2 steps are running complete. Okay, this is pipeline lessons. Pipeline doesn't decrease latency of single task. It increases throughput of entire workload. So multiple tasks operating simultaneously using different resources. So pay attention simultaneously. Potential speed up, number of pipeline stages speed ups reduced by time to fill and join the pipeline. You can find 8 hours and 3.5 hours, which gives 2.3 speed up potential in this example. So we can find pipeline can run up, can lessen the running times. Suppose new washer takes 20 minutes, new stasher takes 20 minutes. How much faster is pipeline? Pipeline rate limited by slowest pipeline stage, and the unbalanced length of pipeline stage reduces speed up. So we can find if the washer and the stasher takes less minutes. In the former, this is 30. In this is 20. So the times of washer and the stasher is less, the pipeline is less. This is one example for pipeline execution. So if you have interesting minds, you can do some searching in website to search sequential and pipeline. Of course, you can do laundry, you can do any other working. So pipeline, in a result, you can find the pipeline is less the running time. Okay, the pipeline data path. You can find pipeline with risk 5. We can find this is the pipeline. This is add operation. This is OR operation. This is SLL operation. So the three operations, the three OP codes are different. So we can use pipeline technology to running and running. So if we use sequential technology, we can find the time is long. If we use pipeline technology, you can find the T instruction is 1000 PS. You can find if we use pipeline technology, so we use the time of pipeline is less and less. So this is important. This is sequential vs simultaneous. So simultaneous is very important. This is one problem. What happens sequential? What happens simultaneous? So you can find if the resource used in a particular time slot, we can find if the resource is single for every step, we can find this is the pipeline technology and the flowchart of pipeline. Resources use of instruction over time. You can find in the red scale, the steps of pipeline is singular, is regular and single. Yeah, this is circuit pipeline, one example. When we calculate cycle time or critical path, we do so between state elements, inputs and output. We can find adding registers between circuit components decrease our critical path and increases our frequency. So you can find this is one example for circuit pipeline. So this is pipeline steps. One is instruction fetch, 2 is decode, 3 is execute, 4 is memory, 5 is write back. This is pipeline with risk 5. So in Chinese classes, we ask them to design pipeline with risk 5 and the multi-pipeline instruction along with data, so control operates correctly in every stage. So if you have interesting minds, you can look some example for pipeline. And the pipeline is advanced technology for CPU. If we find some CPU hasn't pipeline, the CPU level is low. Pipeline control, we can find the control signals derived from instruction, or as in single cycle implementation, information is stored in pipeline registers for use by later stages. So this is one image for pipeline. You can find in some same type, you can find several steps from different instructions. So you can find if the 3 if has different types,
Yeah.
But if ALU and those three have same times, but M is from instruction 1, ALU is from instruction 2, IF is from instruction 3. So these are from different instructions. So the resources they needed is different. Okay, we'll give a summary. Implementing controller for your data path. Ask yourself the questions on the beginning slides. Working stage, put everything together at the end. Pipeline improves performance by exploiting instruction level parallelism. So the parallelism is popular term for pipeline. Each instruction has the same latency, but there's better throughput. So this is one problem. What problems does pipeline introduce? This is the next lecture. Yeah. Okay, this is lecture 13. So you can find in lecture 14, we can find this is the topic. This is the topic for risk 5, pipeline hazards. So parallelism is our topic in lecture 14. You can find this is early smartphone and this is hardware. The hardware is warehouse scale computer. So the warehouse is very important. The warehouse has every service and computers.
Their server.
Yeah, in China, in the cities of China, in Changsha, we have more and more warehouse. If we have more and more warehouse, the power of calculating and every applications are become more and more. So the computer has several cores, memory, input and output. This image is from core. In cores, you can find instruction unit. This is pipeline. Function unit. You can find this is cache memory. In this is logic gates. So we can use logic gates to describe the following. So parallel instruction is one instruction, one time. So, for example, 5 pipeline instruction is the popular examples. Okay, this is the agenda for lecture 14. This is single cycle. A single cycle is 5. Single cycle is simple, and we find the red arrows is related to every component for single cycle. This is pipeline data path. So you can find in pipeline the data path has return because they have a cycle. So you can find data from future states that belong in earlier states can just be where back. So beware back is important. They can return. So this is the return. This is the important technology. Each stage operates on different instructions. You can find in some pipeline. In some pipeline we find the return has needed. So this is pipeline control. Control signals derived from instruction as in a single cycle implementation. Proper information is stored in pipeline registers for use by later stages. So you can find the control is related to other signals. Okay, this is pipeline with risk 5. The example is single cycle and pipeline. We can find every step has every timing, and the register access only need 100 PS timing. And we find RISC-V pipeline resource used by instruction over time, resource used in a particular time slot. This is one skill. Yeah. The DM has instruction and has the resources. Okay. Today is enough, and in next week, in next Tuesday, we continue. So Thursday you can free, and you can read Logisim, the guide of Logisim. You can run and try.
Yeah.
Okay. I'm sorry, my voice isn't good.